So first of all, I would like to thank you for your interest in Q-Chem challenge in QHack. I'm Ryoto Kojima, an engineer at QunaSys. In this video, I will explain why quantum computers are useful for quantum chemistry, and I will introduce some products which are useful for building quantum chemistry algorithms. The contents of this video are as follows. First, I will explain the importance of quantum computers in quantum chemistry. Next, I will explain the criteria for this Q-Chem challenge. Finally, I introduce some useful product for building quantum chemistry algorithm. Okay, so let's start from the quantum chemistry and quantum computers. A quantum computer is a computer that performs calculation based on a principle of quantum mechanics. A quantum computer uses a qubit instead of bit, which is used in the classical computer. So let's see this figure. In the classical computer, 3 bits can represent one of the 8 states, like this. In the quantum computer, 3 qubits can represent 8 states simultaneously. Also, depending on the problem, the quantum computer can solve the problem much faster than the classical computer. One of the promising applications of quantum computer is said to be in quantum chemical calculations. This is an essential tool for modern chemistry research. This is a figure from the Boston Consulting Group report. As you can see, the business value of the chemistry is very high, and the quantum computer will be useful quickly in this chemistry. The basic principle of the chemistry is to understand the molecular structure. For example, as shown in this figure, water is made from the molecule like this. We also know that the behavior of molecules can be described by a theory called quantum mechanics. The study of molecules using quantum mechanics is called quantum chemistry. Also, these microscopic structures are difficult to observe. Computer simulations can be used to visualize these microscopic structures. These computer simulations of quantum chemistry is called the quantum chemical calculations. Let's see the one example to see the importance of quantum chemical calculations. This is a typical high school chemistry experiment. Maybe as you already know, when a lump of sodium is dropped into the water, like this, an explosive chemical reaction occurs. This is a famous reaction, but surprisingly, this phenomenon was understood in 2015 by using a quantum chemical calculations in this paper. So this is one example of the importance of quantum simulation, computer simulation of quantum chemistry. Next is the difficulty of quantum chemical calculations. It is well known that when the size of the problem is n, the amount of the time required for calculation on the classical computer will be exponential, like this. In fact, 40% of all supercomputers are used for quantum chemical calculations, like this figure. The most importantly, it has been found that the quantum computers have the potential to perform calculations in polynomial time. As shown in this figure, a classical computer requires an exponential time, like this red line. But a quantum computer can accelerate it to the polynomial time, like this green line. This acceleration can be achieved with a so-called quantum phase estimation algorithm. This is an algorithm that has a potential to do acceleration to the polynomial time. In fact, in 2018, Google estimates that the calculation of the highest theoretical accuracy, or so-called full CI, of 155 orbits can be calculated in 58 hours with a quantum computer which has a 5 million qubits and error correction. So this is a quantum circuit of this algorithm. However, it will take 10 or 20 years to achieve such a quantum computer of this scale with error correction. So it will take time to reach a quantum computer with error correction. Of course, we cannot just wait. So people are considering to use an intermediate quantum computer, so-called a NISQ device. This noisy means that this device does not have an error correction, and intermediate means that this have a 15 or 1000 qubits. So this is one example of the algorithm used in NISQ device, so-called the variational quantum eigensolver, or VQE. This is a quantum classical hybrid algorithm to reduce the number of calculation steps, like this figure. So this algorithm uses both quantum computer and classical computer. So the quantum computers are expected to be very useful for quantum chemical calculations, and various researchers are studying the chemistry applications based on this quantum algorithm, including the NISQ algorithm. This is the end of the explanation of quantum computer and quantum chemical calculation. Next, I will explain about this Q-Chem challenge. The goal of this program is to build a chemistry application based on your ideas. The screening process is based on these three criteria. The first is originality. The second is how useful your algorithm for quantum chemistry. Here are two examples. Replicate well-known chemical reaction in industrial process, or study of condensed matter phase transition. Of course, the other examples are also possible. The last one is a scalability compared to classical algorithm. Again, here are two examples, but other examples are also possible. We will open the CAMI for all participants. This CAMI is a quantum chemistry software provided by QunaSys. You can use CAMI to build chemistry applications easily. Of course, you are welcome to build using the other products like a penny lane, Qiskit, or SAC, or so on. The CAMI supports all steps needed to test quantum algorithm for chemistry. CAMI simulators can be used for comparing algorithms, preparing calculations on real quantum devices, or calculations can be easily performed on a real quantum device in similar manner as simulator. So this is a figure of the CAMI. As shown in this figure, the user can obtain various calculation results by providing the input data. CAMI makes it possible to do calculations on both simulators and real quantum devices without writing an explicit quantum circuit. So this is an example. VQE is the algorithm to obtain the ground state energy. So by putting the input data like this, so we need to define some input data like a molecule and geometry and basis and so on. Then the CAMI returns the calculation result like this. So this is a result of the VQE. As you can see, we can obtain the result without writing explicit quantum circuit. You can see more detail about CAMI in this document page and more examples from this page. Of course, you can use other products. For example, the penny lane, this is a cross-platform Python library provided by Xanadu. The other is a Qiskit. This is an open source SDK for working with quantum computers provided by IBM. The SAC is an open source framework for programming quantum computers provided by Google. Of course, you can use any of them. So this is the end of the video. Thank you for watching until the end.